today's class we are going to be talking about 2,4 trees. This is another way of representing a dictionary. So, we are going to see operations of insert, search and delete on this data structure, and we are going to have the same kind of performance guarantees as was the case in AVL trees. But we are going to in later classes see how this data structure is useful. So, today I'll just begin with this. So, what are 2,4 trees? They are search trees. They are a kind of search trees, but they are not binary search trees. So, recall in a binary search tree what was happening? The tree was a binary tree. Yeah, each node had at most two children, right. So, this is not going to be a binary tree, that is the first point. So, nodes can have more than two children now. So, these 2,4 trees are also called 2,3,4 trees, right, and I will tell you what this really means. So, 2,3,4 actually refers to the number of children a node can have. So, a node can have either 2, 3 or 4 children, right. Such trees in which a node can have many children, but satisfy a certain kind of search property are called multi-way search trees, right. So, each internal node of a multi-way search tree has at least 2 children, right. Besides the children, so it will have at least 2, which means it could have more than 2 children, right, any number of children more than 2. Each node of the tree also stores a collection of items of the form key, comma, element, right. So, just as in the binary search in the binary tree, in a binary search tree, each node was storing one key and the element there was, let us say, a reference to the element, or the element itself could be stored there, right. If the key was, let us say, student record, student entry number, then the student record associated with the key could also be stored in the node itself. So, in a similar way, we have that in a multi-way search tree, you will have each node containing pairs of this kind, key, comma, element, and how many pairs there could be? More than one, right. In the binary search tree, there is only one such pair in each node, and in a multi-way search tree, there could be more than one. In particular, there could be d minus 1 such pairs or items, right, where d is the number of children that particular node has, right. So, we are just generalizing binary search trees. In a binary search tree, each node has 2 children, yeah, each node could have 2 children, and then there is only one key that is kept in the node, because that key helps us determine if we should go left or right, right. Similarly, here we have d children. If d is the number of children, then you really need to know in the search process whether you should go to the first child, the second child, the third child, the fourth child, and so on. So, you will have d minus 1 different keys sitting in the node to help you determine that. I will soon show you an example, and that should be clear with that, right. And I think I come back to this after I show you the example. Okay. So, this is an example of a multi-way search tree. Okay. As you can see, this node has 2 children, this has 3 children, this node has 2 children, this has actually d children, this has actually 6 children. Yeah. Okay. Now, how many keys are there in a node? The number of keys in a node is 1 less than the number of children that node has. And why is that? Yeah. So, for instance, this node has 3 children and you need 2 keys in the node. The keys determine, the keys in a node determine what set of keys the various subtrees are going to have, right. So, what I am trying to say here is this is key 22. So, everything in this subtree, so this subtree is actually, this is also in the left subtree here, yeah. So, everything in this left subtree here is less than 22 and everything here is more than 22, yes. Is this clear? Everything here is more than 22 and everything here is less. So, if you look at this key, everything to the left of, this is less than 5, everything more than 10, so in the right subtree, so we now have 3 children, right. So, in this first subtree everything would be less than 5, in the last subtree everything will be more than 10, and those in between 5 and 10 would lie in this middle subtree. So, that is the concept, right. Now, you understand why you need d minus 1 keys if you have d children, right. So, everything less than the first key would be in the first subtree. For that, you will have to follow the first child. Everything between the first key and the second key, you will have to follow the second child, and so on and on, right. So, with that, let me go back to the previous slide. So, the children of each internal node are between the items, right. This is what I mean by between, it's in quote. So, you have a certain node, it has the various keys or items. So, if you look at 2 consecutive keys, then all the elements, all the items which have key values between that consecutive pair would be in one subtree. For that, you will have to follow one child. Okay. So, let us get back to this. This is an example of a multi-way search tree, right. And how do you search in such a tree? Searching is similar to the binary search procedure as you did in a binary search tree. So, suppose we are searching for 8, you come down here, compare 8 with 22, 8 is less. So, you go here. Now, you will have to find, so 8 is not less than 5, 8 is not more than 10, but 8 lies between 5 and 10. So, you will follow this, and then you will find that 8 is sitting here. So, it is a successful search, right. So, when you are searching for a key S, you will compare it with K1. K1 is, let us say, the very first key in that node, and K, let us say K d minus 1 is the last key in that node. So, you compare it with the very first key. If it is less, then that means that you have to go to the leftmost subtree. If it is more than K d minus 1, then you have to go to the rightmost subtree. Okay. So, when you are searching for a node, for instance, when we are searching here for 8, we came down, we went left because 8 is less than 22, then 8 lies between 5 and 10. So, we came down here, and then we found 8 here, right. So, when we were searching for 22, we came down the sequence of steps and we found that 22 was not in the tree. Sorry, 12, yes, we found that 12 was not in the tree. Okay. So, in particular, when you are at a node, you have to determine that the key that you are searching for, which 2 keys it lies between, right, and once you have determined that, you will follow the appropriate child down, right. At the 2 extremities, you will check whether it is less than the first key or whether it is larger than the last key, in which case you will follow either the leftmost child or the rightmost child. So, it is as simple as that. So, what would an in-order traversal in this tree look like? That was the question we were at. Okay. So, first, what is an in-order traversal in this tree? So, recall in-order traversal says left, then you print the data of the node, and then you go right. But now, there is no left and right, yeah, because a node can have many children. So, what does an in-order traversal here mean? Right. So, first go the leftmost, then print the key, then go to the next child, then print the key, then go to the third child, then print the key, then go to the next child, and so on, right. So, that would correspond to an in-order traversal, right. So, for instance, in here, if I were to do an in-order traversal, what would I do? So, first I would print 20, no, not first 22, sorry. What would the first? I would come down here, first go left. So, I will first do an in-order traversal on this part of the tree, yeah, which means that I first come in here, I first go left, I will do an in-order traversal here, which means I come in here, I first go left, but there is nothing here. So, then I print the key, that is 3. Then I go to the middle child, nothing there. So, then I print the next key, 4. Then I go to the right child, nothing there. So, that finishes the in-order traversal on this node. Having finished the in-order traversal on this node, I go back to the parent, right, and then I will print this key, yeah, because first I went left, then I print the key, which means I print 5. Then having printed this key, I will now do an in-order traversal of this tree, this subtree here. So, when I do an in-order traversal of this, I will get 6 and 8. Having finished that, I go back here, print this key now, which gives me 10, and then I will do an in-order traversal of this right subtree here, right, and that would give me 11 first, 13, 14, and then all of these. Yeah. So, 17, 18, 19, 20, 21. Now, I have finished the in-order traversal of this entire thing. So, I print the key 22 and then I go right. So, as you can see, you will get the keys in sorted order, right. That is also easy to prove. Why? Because in an in-order traversal, I will first print out all these keys and only then will I print out this key, right. So, which means that in the order of printing, all the keys which are less than this key will appear before and all the keys which are more than this key will appear after, and this is true for every key. So, which means that what you get is a sorted order. Okay. Yeah.
Can any node having more than 2 keys have further children?
Can a node which has more than
For example,
2?
Can 6, 8 have further children?
Yes, 6, 8 could have more than other children also. For instance, I could have some other here, let us say 5.5. Yeah, 5.5 would be a valid node here. Instead of this, I could have just one node with 5.5 here. Yes?
This 5.5 could be in the first node also, means 5.5, 6, 8.
Yeah, so that of course we could have organized it in a different manner, but 5.5 is a valid node here, right. There could be more nodes here. Okay, great. So now let us understand what 2-4 trees are. Okay. So, a 2-4 tree is something like this. What are the properties? Each node has at most 4 children. So, first it is a multi-way search tree. Okay. So, multi-way search tree, which means every node has at least 2 children. Yeah. So, now we are saying each node has either 2, 3 or 4 children only. That is why it is called a 2-4 tree or a 2-3-4 tree. Each node has at most 2, 3 or 4 children. The second important property is that all the leaf nodes are at the same level, right. So, the leaf nodes here are this, just forget these square boxes for now. So, these are the leaf nodes and they are at the same level, they are all at level, suppose we are numbering levels 0, 1, 2 again. So, they are at level 2, right. So, these are the only two properties of a 2-4 tree. Of course, it is a multi-way search tree. So, that is, so a 2-4 tree is a multi-way search tree with these two additional properties. Search tree here, so it will have the property that everything which is less than this key is going to be in the left, everything that is more is going to be in the right. Yeah. So, this is an example of a 2-4 tree. As you can see, this node has 3 children, this has 2. There is no node with 4 children, but you could also have had a node with 4 children in it. Yes, it's clear to everyone. What is the height of a 2-4 tree now? Okay, do not read from the slide. Tell me, why should the height of the tree be at least log n to the base 4 and at most log n to the base 2? Right. So, what is the worst case? When would the height of the tree be maximum? When everyone has 2 children, right? And when it is in that case, everyone has 2 children and all the leaves are at the last level. Then it's basically, it's exactly a complete binary tree, and a complete binary tree we have argued that the height is log n base 2. There was a +1 -1 somewhere, I forget where it was, but it's something like that, right, log n base 2. Right? That's the setting when the tree height is maximum. The tree height is minimum when every node has 4 children in it. Yeah, because then the nodes are closer to the root, right. You will have 4 and then 16 at the next level, and then 4 to the 16 to the 4 at the next level, 16 times 4, 64 at the next level, and so on and on. Yeah. So, once again, if you do the same analysis, you will find that the height of this tree is log n to the base 4. So, the height of a 2-4 tree on n nodes always lies between these two quantities. Yeah. It is either log n base 2, it lies between log n base 2 and log n base 4. Log n base 4 is essentially half of log n base 2. Yes. So, basically the height of the 243 lies between half of log n and log n. Okay. Now, you can tell me how much time it takes for search. How much time does it take to search in a 243 then? Huh? Why log n? How do we search in a 243? It's a multi-way search tree, right? So, if I am searching for a particular key, let us say suppose what do I want to search? I want to search for 11, let us say. Oops. Suppose I want to search for 11, 1 second. I want to search for 11, I came here with 11, right. Where would I go? Compare 11 like with 12, I come here, right. Let me change color. 11 I am comparing with 10, so I go right, and then I find 11 here. So, I found 11. Yeah. So, how much time does it take for me to search in a 243? Height of a tree. Is there something more that I need to do? It is correct, right? It is order height of the tree. I have to compare within each node, right? Because when I am searching for 11, I have to essentially now compare against how many keys could there be in a node? How many keys could there be in a node? A node, we said, has how many children? 4. If it has 4 children, how many keys would it have? 3. The maximum number of keys therefore is 3. If it has 2 children, how many keys do I require? 1, right. So, a node has either 1, 2 or 3 keys. So, when I search for a key and I come with a key, then I have to compare it with this node, with this key, with this key and with this key. So, I might require 3 comparisons in all, right, to determine which particular branch to take out. So, I might require 3 comparisons. So, the time is 3 comparisons within a node times log n, because that is log n is the number of nodes I would be visiting, order log n. Yeah. So, order log n is correct, but you have to be careful about this, right, that within each node you require more than one comparisons. In a binary search tree you required only one comparison, but now you could require up to 3 comparisons. Great. Why 3 log n? So, he is asking me why did I say 3 log n? Well, when I am searching, I start from here, yeah, start at the root, and then whatever key I have, I compare it with the keys in a node. So, here this node has only one key, but it could have had 3 keys in it. Then I have to compare against each of those 3 keys to determine which particular branch to take out of that node, right. There are, if it has 3 keys, then there are 4 different branches. Which should I take? To determine that, I need to make 3 comparisons. Great. So, now let us look at insertion in a 243. So, I have this largish example that I am going to be using to show you the process. Okay. So, is this a 243? This has 4 children, this has 4, this has 2 children, this has 2 children, and this last one also has 2 children. I have shown the node with 3 locations in it, right. So, each node will have space for 3 keys, right, and 4 pointers. So, it has only one key, but I am just shown each node as having space for 3. Okay. So, the first element I am going to insert is 21. So, how do we insert? We insert just as in the case of a binary search tree, right. So, first we will search, and wherever our search terminates, if we found that element, then you would say that okay, it already exists, we will not insert then, right. But wherever the search terminates, we would insert the element there. So, let us see, 21 I am trying to insert. So, 21 I come and compare. So, here 21 lies between 13 and 22. So, which means I am going to take this branch out. So, I take this branch out, I compare it against 18, it is larger than 18. So, I am going to take this branch out. So, I take this and it goes and sits in that particular node. Yeah. Why does it go and sit in this node? Why didn't I compare with the 20 and say, okay, let me go down further?
The empty space.
Yeah, this is a leaf node, right? If I, when I hit a leaf node, you know, if I had, okay, I could have also have said it, okay, I compare it with 20, then I try to go right, but right node is empty. The right pointer, there's a null pointer because it's not going down any further. So I know that this is the place where I have to insert, and this is empty. There is space here, so I just put it here.
Could you put it next to 18?
Yes, sir.
Sir, if the
So why not
child is full,
Only a leaf child.
next to 18.
No, we would not put it next to 18. We would continue
Till
till we can't go any further. This is what happens in a binary search tree, right? आप insert करते हैं तो आप compare करते जाते हैं, you keep comparing till you hit a null pointer and then you put it there. So till we hit a null pointer, so we compared it 21 with 20, let's say we were trying to go right, but this is a null pointer, and so we put the node here then. Okay. Now you are wondering, how am I going to use this space? We will see how we are going to use this
Sir,
space.
had this been already filled, sir, then what would we do, sir?
What if this was already filled?
Yes, sir.
अगर यहाँ पे ऑलरेडी था एक, तो फिर हम यहाँ डाल देंगे.
सर ये भी fill होगा.
अच्छा, तो उसके लिए you will have to wait till the next slide. Not next week, but next slide, huh? Okay. So if there is empty space, no problem. You can do the insertion. Let's say we now try to insert 23. Okay, so 23 lies between 22 and 32. So we are going to take this link out. So we took this link out. 23 is less than 25. So we come down here. Okay. So 23. So in a node, we will try to keep the keys in inserted order. We have to keep them in sorted order, sorry. Yeah. Because only then will we be able. So 23 should come at this place. So what should I do? Move 24 to the right, and 23 will come at its place. Yes. So insertion always actually happens at the very last node, at the leaf nodes. So here, the other way I could think of it as 24 was here, I compared 23 with it, I tried to go left, that's a null pointer, so that means I have to insert at that node itself. Okay, now we are trying to insert 40. There should be no problem with 40. 40 is more than 32, so I go right. I come here, 40 is more than 35, so I again go right. And there is space here, so I compare 40 with 39. It's a null pointer, so which means I have to put it right here. There is space, so I put it. Okay. So now let's say I was. So now if I'm trying to insert a node. So now the question, right, that if I'm trying to insert a node and there's no space available, I'm trying to insert a key and there's no space available in the node in which the key should go, then what do I do? And that's an example. So when I'm inserting 29, that's the kind of a thing that would happen, right? So 29 between 22 and 32, so I follow this. 29 more than 25, so it wants to come and sit here between 28 and 30, except that there's no space here. So this is what we are going to do. We are going to split the node. Which node are we going to split? This node. The one containing 26, 28, 29 and 30. We are going to split it into two. Okay. Let's say these are 4 keys. The 2 smaller ones will go to the left and the 2 larger ones will go to the right. Okay. And we will remove this node. Now we need to link up this node, right? This should be children of this guy here. Yes, because these were all originally children of this node, right? So this should also be a child of this node. But now it's going to have 3 children. But how many keys are there? 1. So we need one more key here. Right? If it has 3 children, it should have 2 keys. So which key should I put here? Okay, I'm going to promote ये जो मैंने split करके ये जो 2 nodes बनाए थे, इनमें से एक की I'll promote up, right? So it's best to just promote up 28 here. Okay, so that's what
The 29 if you
I'll promote up 28 here. I could also have promoted up 29. You understand why 28 and why not 26? If I had promoted up 26, what would be the problem? Then the search property would not be valid. Yes? So, I have to promote either the largest key from this node up here or the smallest from here. I have to promote that up here. Everyone with me? Right? So, this will become the new structure. So, we have promoted one key to the parent and inserted that key here. We could insert the key into the parent because there was space in the parent. But it might happen that when I am trying to insert a key into the parent does not have any space. फिर क्या करेंगे? पेरेंट को स्प्लिट कर देंगे. तो देखते हैं क्या होता है जब हम 7 को इंसर्ट करने चलते हैं. ठीक है, 7 less than 13, so we have to go left. 7 between 3 and 8, so we should follow this second child, we should follow this second pointer. So, it should come here and we want to put it here, except that there is no space, so we will split this node. 2 nodes created, 4, 5 go to the left node, 6, 7 to the right node. Okay? We get rid of this one now. These are the 5 children of this node now. ठीक है, तो हमने क्या कहा था, ये वाला जो हमने क्रिएट किया है जो स्मॉलर है इसको हम प्रमोट कर देंगे. तो वो करते हैं प्रमोट. 5 को हमने यहाँ प्रमोट कर दिया. ठीक है, अब वही प्रॉब्लम हो रही है कि यहाँ पेरेंट में भी जगह नहीं है. So, if the parent node does not have sufficient split, then it is split. Okay? So, we split the parent node into 2. 3 and 5 will go to the smaller one, 8 and 10 will go to the larger one, to the right, to the other node. Okay? Now, I have 1, 2, 3, 4, 5 children, right, and they have to be made children of these guys. Okay, and one of the smaller के जो highest key है that has to be promoted up. Yes, because when a split happens, then we take the key of the largest key of the smaller node and promote it up. So, we are going to create, so the left 2 would go into, so these two left children, the first 2 children would be made children of this node, the right 3 would be made children of this node. Why 2 of this and 3 of this? Because 5 is going to be promoted up, right. So, that means that there is only going to be one key left here, which means that this can have only 2 children. The first 2 children will go here. 5 is going to be promoted up, so this will have 2 keys, which means 3 children. So, these 3 would be its children, and we promote 5 up, right. So, we split this node, यहाँ पे जो node था that we split first, then we went and split the parent, and now we will see a split happening here also, because this does not have any space. So, we will split it into 2, 5 and 13 would go into one node, 22 and 32 would go into the other node. This will disappear, and now 1, 2, 3, 4, 5, these are 5 children. So, 13 will get promoted up now, remember, right. So, the first 2 will become children of this, and the next 3 would become children of this, and 13 gets promoted, but where does it get promoted? There is nothing at above, right. So, we will create a new root. So, eventually we may have to create a new root, which is what is going to happen now. So, we create a new root, 13 goes up there, and these 2 become the children of this, right. So, if we create a new root, the height of the tree increases by 1. Is everyone with me? You understand the procedure, right. So, you try to, so first you will come down the tree till you hit a leaf, you will try to put the key there. If there is space, great, nothing to be done, very simple. If there is no space, then you split that node, yeah. And then we decided that the 2 lower keys will go to one node, and the 2 higher keys will go to the other node. The largest key in the lower part would be promoted up, right. So, when we split, there are 4 keys in a node. There were 4 keys, 4 की वजह से ही split करना पड़ा हमें. So, which means the second key of those 4, yeah, is the one which will get promoted up. Promoted up means we are trying to insert the key into the parent node. If you are successful, if there is space, no problem. Otherwise, repeat the split process on the parent node. Split it, right, and this split might cascade all the way up to the root. If it cascades up to the root and the root also gets split, then we have to create a new root. That is it. Yeah? Any questions? Great. How much time does insertion take? So, search was very clear. For search, we said it will take order log n time. How many splits can there be in the process of insertion, right? It is at each level we might be doing a split. How much time does one split take? How much time does it take for me to split a node? I will create some two nodes, 2 keys यहाँ copy करने, 2 keys वहाँ copy करने, 4 pointer change करने, constant time, independent of the number of nodes. Yeah. So, each node split takes constant time. So, the total time is order log n. सबके समझ में आ रहा है? Great. So, now let us look at deletion. Right. So, suppose I wanted to delete 21. So, first, as in the case of a binary search tree, right, first you will have to search for 21, find out where the key is. In the case of a binary search tree, recall deletion required 3 different cases. If the key was at a leaf, then you just knocked off the leaf, nothing to be done. If it was at an internal node, then you had to, then we distinguish between 1 child and 2 child. The 1 child case is not really happening here, right. So, it is only the 2 child case that we have to be worried about, right. So, if it is at an internal node with 2 children, then what did we do? We found the successor or the predecessor of that key. Let us say we found the predecessor, and we move the predecessor to that and delete the predecessor. That is what we were doing, right. So, we are going to do something similar here. Let us see, suppose I wanted to delete 21. So, 21 there is no problem, because 21 is in a node, right. So, we will search for 21. So, we come down here, go right, go left, go right, and I find 21 right here. Now, why is there no problem deleting 21? It is in a leaf node. I can just remove it, and I can remove it without violating the property of a 2-4 tree. In a 2-4 tree, we require each node has at least 1 key and at most 3 keys. So, after deleting, this will still continue to have 1 key. So, no problem. Okay. So, that is what is going to happen, sorry. So, I have not shown the process, but this 21 will get deleted. We just knock it off from here, nothing to be done. Now, if key to be deleted is an internal node, is at an internal node, for instance, suppose I were trying to delete 25, right. So, I search for 25, I find 25 right here. Yeah. So, what do? I am going to swap it with its predecessor. So, what is the predecessor of 25? How do I find the predecessor of 25 now? In the case of a 2-4 tree, I will go left and then keep going right. So, यहाँ पे तो कुछ है नहीं, I go left and then I find the largest key in this node. Yeah, I find the largest key, it is 24. So, predecessor of 25 has to be 24. So, I am going to swap these two, okay, and then I am going to remove the 25 from here. It is the same thing. Now, I can remove the 25 from here. Why? Because it is in a leaf now already. Yes, and there are there were 2 keys in this leaf. So, if I remove one, there is no problem. Note that the predecessor will always be in a leaf in this case. Not in the case of a binary search tree. Let us check this point out. In the case of a binary search tree, the predecessor of a node need not be a leaf node, right. Suppose this was my binary search tree, this was a node 10, I am finding the predecessor. So, I go left and then I go right, right. So, this could have been my binary search tree. So what would be the predecessor of 10? It would be this guy, right? Yes, but this is not a leaf node. But here the predecessor will always be a leaf node. Why?
Because these two will be at same level in this. Like
Why would the predecessor always be? So how do I find the predecessor here? I go left and then keep going right. Keep taking the rightmost child. So when will I stop?
When we get to a leaf
No right.
there is no right children.
What?
So there is no right.
When there is no right child. When there is no right child, what does that mean? Right, when my right child is null, then that means that all the children are null. Right, because I cannot have a situation in which there is a node which has a key, it has no right child, but it has a left child. This is not permitted at all here, right? If there is a key, then we have we will have two children then. If there were two keys, then we will have three children, and so on. Great. So my predecessor would always be in a leaf, so I would just remove that leaf node and I would be done. So that's what I do. Now I have to recall I was deleting 25, so I swapped 24 and 25, and now I have to just get rid of 25. So I get rid of, oh sorry, I just have to get rid of 25, so I will get rid of 25 by that, right. So 25 will dissipate from here. It's a very simple case. So as you can imagine, problem will arising when I am in a leaf, I am trying to delete a key from a leaf which has only that one key in it. Then that leaf becomes empty. What do I do now? Right. So let's look at that. So if after deleting a key, a node becomes empty, then we borrow a key from a sibling. And let's see what that means. So suppose I am trying to delete 20. So I search for 20, I come down in this manner, right. I reach here. Now if I delete 20, so 20 is removed. Problem is this is an empty node, not permitted. What will I do? Borrow from sibling. What does borrow from sibling mean? Well, this guy has only one sibling, this. So can I borrow 15 from here to here? No, disaster, right? Because search property is not going to be valid. So it's going to, we are going to do something like a rotation, like we did in an AVL tree. What does that mean? 15 goes up and 18 comes down. 15 goes up and 18 comes down. Okay? And now everything is fine? Yeah? Okay. So then the next thing you are wondering is, if I cannot borrow from my sibling? Yeah? If I cannot, when can I not borrow from my sibling? When the sibling has only one key in it. Right. For instance, now if I were trying to delete 18, then that would be a problem, right. Let us see. So if sibling has only one key, then we merge the sibling, we merge with the sibling, we combine with the sibling. Okay. So suppose I was trying to delete 23, right. So again, so 23 is right here. If I delete it, this is an empty node. So I try to borrow from a sibling, right. Okay. Now there is a small catch here. इसके कितने siblings हैं? 1 and 2, right. But I cannot borrow from this one. You see why? Because for the search property it will get, because you know if I were to promote something, then 28 is going to come down, but this is going to jumble this thing. So when I say borrow from a sibling, I really mean an adjacent sibling. If I can borrow from here. So when I am here, I can borrow from here. If I am here, I can borrow from here. If I am here, I can borrow from here or from here, right. But here I can only borrow from this guy. Everyone understands why this is required? So I try to borrow from here, but if I borrow from here, that is 26 goes up and 24 comes down, this is going to become empty. Yeah. So that's not going to solve our problem. So what we are going to do is merge. These two are going to merge, combine. But if these two combine, then the number of children here of this guy will become 2, which means यहाँ पे तो एक ही की होनी चाहिए, तो यहाँ की एक की हम नीचे ले आएंगे. So the key in the parent node which separates these two siblings, which is this key, which is separating these two siblings, is going to move down into the merge node. Okay, so let's see. I create a new node, which is the merge of these two nodes. This moves down, and this also is. These are the only keys in this new node, right? Because there was one here, there was none here, and there was one here. 2 keys in all, so they come and sit here like this. These two will now disappear, and this becomes a child of this now, right? तो यहाँ थोड़ा सा हमें जगल करना पड़ेगा, because हम एक ही यहाँ पे की बची, तो इसको हम यहाँ रखते हैं, तो इसको यहाँ रख देते हैं, और ये इसके चिल्ड्रन हो गए. ठीक है. Okay. Now what can happen? So essentially what we have done is we said we are going to, one of the keys from the parent node is going to come down. But what if there was only one key in the parent node? Right, the same as before, right? जैसे हम insert में कहा था कि अगर हमारा parent node भरा हुआ है तब हम क्या करेंगे, उसको split कर देंगे. अब हमारा parent node अगर खाली हो जाता है क्योंकि एक की वहाँ से नीचे आई, तो उसको अब क्या करेंगे, सेम जो हम यहाँ कर रहे हैं अभी तक, वो अपने सिबलिंग से बोरो करने की कोशिश करेगा. सिबलिंग से बोरो कर सकता है तो बहुत अच्छी बात है, नहीं कर सकता तो मर्ज कर जाएगा सिबलिंग से, और फिर अपने पेरेंट से एक नीचे ले लेगा, एंड सो ऑन एंड ऑन. ठीक है. सो मूविंग अ की डाउन फ्रॉम द पेरेंट नोड corresponds to deletion in the parent node, deleting a key from the parent node. This procedure will be the same as that we've done so far in this leaf node, but it can lead to a cascading. Right? Cascading as in उसने अपने पेरेंट से बोरो किया, उसका पेरेंट अब खाली हो गया, तो उसको जो है अपने पेरेंट से बोरो करना पड़ा, उसका पेरेंट खाली हो गया, ऐसे ऐसे ऊपर तक जा सकता है. राइट, एंड विल सी दैट हैपनिंग इन दिस एग्जांपल नाउ. अब हम 18 को डिलीट कर रहे हैं. ठीक है, 18 को डिलीट कर रहे हैं, तो वही पहले आप 18 को सर्च करते हैं, यहाँ आते हैं, 18 गायब हुआ यहाँ से, ये नोड खाली हो गया, ये अपने सिबलिंग से बोरो करने की कोशिश कर रहा है. इसके कितने सिबलिंग हैं? एक सिबलिंग है ये, पर इसके सिबलिंग में भी एक ही की है, तो बोरो नहीं कर सकता. तो क्या करेगा, सिबलिंग से मर्ज करेगा. तो एक ये नया मर्ज नोड बनाया हमने, इसमें ये की आएगा और इनका जो सेपरेट कर रहा था इनको, एक पेरेंट से एक की नीचे उतर के आएगी. ठीक है, तो ये दोनों यहाँ आ गए. अब ये दोनों गायब हो गए. दिस इज द ओनली चाइल्ड लेफ्ट ऑफ इट्स पेरेंट. राइट, पर पेरेंट अब खाली हो गया. तो पेरेंट खाली हो गया, तो अब ये क्या करेगा, ये बोरो करने की कोशिश करेगा इसका इकलौते सिबलिंग से, पर द सिबलिंग इज ऑल्सो ओनली वन की. सो वी आर गोइंग टू मर्ज विद द सिबलिंग. वी आर गोइंग टू क्रिएट अ न्यू नोड which is going to get the sibling key and the key from the parent, which is 22. So this is the situation now, right? And we will delete this and this. This ये भी खाली हो गया, तो ये दोनों खत्म हो गए, ये सब खत्म हो गए. ये 3 चिल्ड्रन जो अब बने, ये अब सब इसके चिल्ड्रन हो जाएंगे, ये जो हमने बनाया. ठीक है, पर अब ये हमारा खाली हो गया है, तो ये अब फिर से इससे मर्ज करेगा. तो इसके लिए हमने एक और नया नोड बनाया, ये दोनों इसमें मर्ज हुए. ठीक है, और ये भी खाली हो गया, तो इसको भी हमने अब हटा दिया, और इसके अब ये जो 3 चिल्ड्रन हैं, ये इसके चिल्ड्रन हो गए. ठीक है, अब ये बचा है खाली, तो इसका क्या करें, इसको हटा देते हैं. ठीक है, तो हमारी हाइट ऑफ द ट्री एक घट गई अब. Right? So because of these deletions, the height can reduce by 1. Right? After all, we said height जो है कम से कम log n base 4 होगी. अगर आपके delete करने के बाद log n base 4 जो है उससे कम चला गया आपका, right? Log n base 4 is less than what it was, then that means the height has to shrink, and that would happen. Yeah? और insertion में height बढ़ सकती है. ठीक है, so everyone understands this procedure, right? There are just very few concepts that we have really एंड इंसर्शन में स्प्लिट होगा और डिलीशन में दो चीज़ें हैं, राइट एक तो पहले तो वो बोरो करने की कोशिश करता है और अगर अनसक्सेसफुल है बोरो करने में तो मर्ज कर जाता है, ठीक है। शुरू में ही क्यों नहीं मर्ज कर जाता?
So then it may need to, if it has a sibling as 3, then it may
इफ इट हैज द सिबलिंग एज 3 तो 3 सिबलिंग से लेंगे और एक ऊपर से भी लेना ही पड़ेगा, है ना, तो वो 4 हो जाएंगे, फिर आप उसको स्प्लिट करोगे बैठ के, ठीक है। तो जो है नो पॉइंट इन डूइंग दैट। सो फर्स्ट यू ट्राई टू कॉपी, ट्राई टू बोरो, इफ नॉट सक्सेसफुल देन यू मर्ज। Great. So let's conclude today's discussion. Height of a 2-4 tree we've seen is log n, right? This should actually be a theta of log n. Why? Because it's at least log n by log n base 4 and at most log n base 2, right? So as far as deletion was concerned, we have not looked at the running time for deletion yet, but you can see that that is also log n. Why? Because first we come down the tree to search for the key, that's log n, right? And then we keep moving back up. At every step we might go all the way back up to the root, right? So another log n steps. Each step we are either borrowing one from a sibling or we are merging with the sibling, but all of them are constant time operations, right? Borrowing would correspond to एक अपने की ऊपर मूव किया, एक नीचे लाए, constant time, right? और थोड़े से pointers change किए. So what we've seen is that search, insertion, deletion all take order log n time in a 2-4 tree. So why did we come up with this very complicated data structure? So why are we doing all of this? Okay, so well, they are fun, right? No? Okay, you don't buy that. There is another reason. We are going to see another data structure called red-black trees. Okay, and that's also a very fast data structure for implementing dictionaries. And what we are going to see is that what we learnt about 2-4 trees today is going to be very helpful in understanding how the red-black trees function, right? So we are going to look at this in the next class. So with that we end today's discussion on 2-4 trees.